Hey, welcome back. A few words about the project. And the project should culminate with the drawing of the gear, or rather the pinion shaft. The shaft, it's solid with the pinion that drives the large gear, and that gear is also the flywheel, and it's mounted directly on the crankshaft of the press. I'm emphasizing this because industry people that come in, members of the advisory board, oftentimes say that students do not know how to actually read mechanical drawings, not to mention doing correct mechanical drawings. So here you have, and I send this to you, you have a pretty complete drawing of a shaft very similar to the one that you're going to design. I do have, let us see, so it was attached, and I can, let's see, it should be on teaching and for this class and projects. Yeah, projects. So I sent you this is attachment, and if I make it a little bit smaller, so it shows where the two bearings will go, the gearing forces. This is the tangential force, the torque transmitting, the power transmitting force. This is just reaction force coming from the meshing of the pinion with the large gear. I said that pinion should be equally distanced between the two bearings at A and C, and I even recommended what the distance in terms of pitch diameter should be between the bearings. I don't recall the exact recommendation. It's in the project specs. This is the force that comes, it's due to the belt, and it's at an angle, and you selected the angle of the belt relative to the horizontal when you decide upon the specification for your project. There is a key here that serves to attach the driven pulley. The one that will be custom made, it's not one that's from catalogs. However, the one that goes on the motor shaft should have the size as available from suppliers. But look at the proportions. I would consider this to be a proportionate gear shaft. You're going to do calculations for the required minimum diameters at the bearings, and also where the pulley goes. There will be a torque transmitted between D and B. There will be bending moments at the bearings. At least this one, you have negligible bending, but you have shear caused by bending. And I told you from the book by Mott, what sample problem to consider in sizing the shaft. Now you would need to know what the material for the shaft is, and the material for the shaft comes from the calculations for a gear. So the gear pair. So the pinion would be made of a carbon steel that is hardened, has to have certain minimum hardness to satisfy the contact stress requirements, in addition to the bending stress requirements. Okay, so sizing the gears first, and only then you finalize dimensions of the shaft. Of course, the shaft diameter cannot go bigger than the addendum, rather the dendum circle of the pinion. Actually, you'd have to have a little bit extra difference in diameters between the so this would be the dendum circle, and you want to have some difference in diameters here. Again, the pinion is part of the shaft. It's not separate. It's not assembled with a key, like some examples in chapter 9 of the book by Mott. So back to the sample drawings of shafts that I have. Notice for this one, the bearing, one bearing will be here, and the other bearing will be at this location. Likewise, yours, you have a pinion that is solid with the shaft. This is not very clear. Is it a splined? I don't see the detail. If it's a splined and or it has a key. A key is not appearing. It might be a spline. Yeah, it's a spline end of the shaft. I question the need for this groove for a retainer ring. You may go around not having it by just providing the right size step. Notice the various tolerances. So there is where the bearing goes, there is tolerance specified, not elsewhere. There are tolerances on the addendum diameter of the pinion. There's also tolerance to radial what is this, wobbling? Don't recall exactly. So this is tolerance that says that as you say you have a dial indicator and you run it against the this diameter as the shaft's rotating, and the deviation shouldn't be bigger than 0.01 millimeters. There is, for location purposes, there is a tolerance to where the bearing is, but it's in your case you will not have to have this. And likewise, this is 0.5 millimeter. This is clearly so plus minus 0.5 millimeter, 4 millimeter. That's easily achieved. No need to specify that kind of tolerance. The main so on every mechanical drawing you would have to see first the maximum size information, so that a technologist could choose the stock material, or the machinist. So you'd need to know the full length, you need to know the maximum diameter. They should be there. As you can see, I have 1, 2, nothing wrong with them, I just check them. And then this one is so specified. There's no dimension here. It comes out from subtracting from the full length, this one, and this one, and this one length. Very important, on both ends of the shaft there are center holes, or at least, so let's see, we have center hole at this end. Is there any information about center hole? So it says 2 holes, yes, so there are 2 center holes. They're pretty much standard. You can specify them in all this detail, but by just listing the size number of the center hole, that would be enough. Also, among the scan documents that I have here, so like I said, they are standardized. This is a German standard, EIN. And the specification for the center hole could be just based on the form of and the size, and really this is the shape of a center drill. So center drill is going to generate this hole Form A right away. Any additional feature could be obtained by the machinist, by the lathe operator. Okay, so this was one, and I think we discussed most of what's important here. Again, don't over specify tolerances. Every tolerance that you put on the drawing requires the machinist to take measurements, and that can be time consuming. So for your application, given the size of the punch press, I would say that you won't need, if we go back to the original drawing, so you won't need at most one of these, but not a full set of tolerance. I'm going to project or bring up a drawing by a student and show you where he got it wrong. This is another drawing from a Romanian source. Center holes at both ends. They just refer to the standard. No detailed drawing of it. There is a bearing. There is a bearing here. There's another bearing here. There is a bearing here, and there is another one here. This one is located with a retainer ring. I'm a bit more okay with the retainer ring here because it's not an area of the shaft that's loaded in bending. For the other example of retainer ring, we're in this area which is loaded in bending. Tolerances where bearings go. This is an area that accommodate, by just looking at the tolerance it's specified. So this is where a seal, a rotational seal, is going to make contact with the shaft. And then a key with for a belt sheave. The same, I don't remember the exact name, wobbling tolerance specified. And then there was on the other drawing too. So there are surface finishes. This is a metric drawing. So we have on the flank of the tooth 1.6 finish. That's achieved with grinding, and this is 0.8. Necessarily has to be ground between centers. Again, we have center holes. This is where bearings go. This one here, 12.5. It's the surface finish of the surfaces that don't have a tolerance specified. Maybe this actually, it's missing information. So if you have a tight tolerances on a surface, on a portion of the shaft, you would have to have surface finish that matches that tight tolerance. It's 12.5. I don't think it's the finish of this one. It's probably going to be comparable with 0.8, because again, this is where the where it's that seal, the rotational seal goes. Okay. Fillet ready, full length. This is the close linear or longitudinal dimension. And you can see there's no number to it. So if you specify this one and this one, and of course you have to have the full length in this, it's what's coming out from observing these two dimensions. Okay, chamfer, information for chamfer. A lot about how mechanical drawings should be done is, of course, explained in textbooks on engineering graphics engineering drawing and design. I don't know if you're familiar with any of these, or if you have used any of these for your foundations too. If not, maybe you can find something that's available for download. Before we move forward, I want to project a drawing by a student. It was one of the more complete submissions. I said I'm making it mandatory. You'll lose significant amount of points if you don't have drawing of a shaft. Now, let's look at what he got wrong. So firstly, his gear is helical gear. I don't know, clearly for your project, the recommendation was for the pinion, the gear to be spur gears with straight teeth. There is a key at the end, yes, but is probably from his calculations resulted this small. It doesn't look right. Chamfer is ridiculously big and interferes with the key. So even if the calculated length of the key is only this long, you make it full length. And then the shaft is too slender. I don't know why he has to have it this long. Does not make sense. Yes, a bearing goes here, a bearing goes here. Fillet radii on a shaft, they are difficult to achieve at this form, not at the steps. So radii like this, you just get it by or with the using the right tool. Okay, so this could be just the radius of the tool, used on the lathe when turning. If you have a fillet, if you want to have instead of a chamfer, you have a fillet like this one. This is complicated to get. Chamfer is much easier to, and you would need a chamfer for the ease of inserting the bearing. So we have a bearing here. I don't know why he decided to have multiple steps, and most and even more questionable is why he had to have, because these are non-assembling surfaces. So the torrents here and the torrents here, they're wrong, or they shouldn't be. And they are pretty tight, and these are free surfaces, non-assembling surfaces. The other bearing goes here. Yes, you need to have tolerances, but this one is just free surface, and you don't need any kind of tolerance. He put tolerances in pretty tight tolerances on any on every of these lengths here, and usually you don't have as a closing dimension the one that's an assembly. Maybe one of these free lengths could have been. So have a dimension here and not one here. I don't have the drawing tools for PDF. So again, all these tolerances are very expensive to satisfy. You have so for this 8-inch, if you want a tolerance of 0.005 length, that will be very difficult to get. So it's much easier to satisfy the tolerances on a diameter. You put it on the lathe, and you have the dials on the on the lathe that you can use to go close to these tolerances. But when it comes to this big length, and you want to be this tight tolerances, it'll be very hard to get. Okay. So yeah, he overdid it, and the shaft is too slender. If the pulley goes at this end, with only this long key, again, doesn't make sense to have this long slender end with only this little key. Where is the key? The key will be over the entire length, more likely. So again, it does not look proportionate, does not look right. Too many tolerances. I'm not seeing the centering holes. You need those to get these tolerances on the grinding between center machine. Okay, so use the others as examples, not the student's drawing, which I'm not providing you with a copy anyway.